Welcome, and let's talk about SymmetroBloom 4B, a geometric model of 16 symmetries for final term project. So this is the part 2 of our presentation, and again, I am Jerry Abigail Asmakay from BS Ed Math 3A. So for our task 2, explore its subgroups and draw a lattice diagram relating the different subgroups. So I have listed here the subsets of the group 4B under the binary operation star. But take note that I haven't listed all the subsets of the group of order 16 when looking for its subgroups since the number of possible subsets is quite large. Instead, I focus on identifying the subsets that are more likely to satisfy the group properties. So we have here a theorem. A subset H of a group is a subgroup of G if H is closed under the binary operation of G. The identity element E of G is in H. And for all A element of H, it is true that A inverse element of H also. So a subset must satisfy the subgroup theorem. That is, it must be closed under the group operation, contain the identity element, and include inverses for all its elements in order to be considered a subgroup. Now let's check each subset. So we have B sub 5 and the element of B sub 5 is A and R. The result, we can see that the result remains within the subset. Therefore, the subset is closed under the operation, satisfying the first condition for being a subgroup. Next, we can see that there is a row that matches the outer top row and a column that matches the outer left column. And the identity element A of G is in H. So it satisfies the second condition. We know that the inverse of A is A and the inverse of R is R. Since both elements have their inverses within the subset, the inverse property is satisfied. Therefore, B sub 5 is a subgroup. And then let's have B sub 9. The result remains within the subset. Therefore, the subset is closed under the binary operation of G, satisfying the first condition for being a subgroup. And then there is also a column that matches the outer left column and a row that matches the outer top row. And their intersection is A. And the identity element A of G is in H. So it satisfies the second condition. Next, we know that the inverse of A is A, and A is an element of P sub 9. And the inverse of L is L, and L is an element of B sub 9. Therefore, it satisfies the inverse property. So, B sub 9 is a subgroup. Now, instead of checking all two element subsets one by one, we can rely on a key idea. So here is the key idea. It says that any subgroup of order 2 has to look like the set containing E and A, where A squared is equal to E. We can see that B sub 10, B sub 11, B sub 12, B sub 13, B sub 5, and B sub 9 contains the identity element. We know that L, O, V, E, M for PH is its own inverse. Therefore, that already means it has the identity. It's closed and each element has an inverse. So any subgroup of order 2 will always look like this and automatically follows the subgroup rules. Therefore, B sub 10 is a subgroup, B sub 11 is a subgroup, B sub 12 is a subgroup, B sub 13 is a subgroup. Same with B sub 14, B sub 15, and B sub 16. B sub 15 is a subgroup and B sub 16 is a subgroup. Now let's check B sub 17. So we can see that the resulting elements are within the subset. And there is a row that matches the outer top row and a column that matches the outer left column. Their intersection is A, and the identity element A of G is in H. So it satisfies the second condition. Next is the inverse. We know that the inverse of A is A, and A is an element of B sub 17. The same with R and L. And the inverse of M is M, and M is an element of B sub 17. That's why it is a subgroup. And then let's check for B sub 18. And the resulting elements are within the subset. It satisfies the closure or the first condition for being a subgroup. There is also a row and a column that matches the outer top row and outer left column. So the identity element is A, and the identity element of G is in H or B sub 18. So it satisfies the second condition. For the inverse, we already know that the inverse of A is A, the inverse of R is R, and O, and for its inverse is itself. So B sub 18 is a subgroup. B sub 19, we can see that the result remains within the subset. Therefore, the subset is closed under the operation, satisfying the first condition for being a subgroup. And then the identity element A of G is in H. So it satisfies the second condition. We know that the inverse of A is A, R, V, and T is itself. So it satisfies the third theorem. So B sub 19 is a subgroup. And then we have B sub 20. So we can see that the resulting elements remains within the subset, and the identity element A of G is in B sub 20, and the inverse of A, R, E, and H is itself. So B sub 20, a subgroup. And then now let's check for B sub 21. We can clearly see that the resulting elements are within the subset. Therefore, the subset is closed under the operation of G, satisfying the first condition for being a subgroup. Next is the identity element. There is a row and a column that matches the outer top row, and a column that matches the outer left column. So their intersection is A, and the identity element A of G is in H. That's why, or that indicates that the second condition is satisfied. Next, we know that A and R, the inverse of A and R is itself, while S, the inverse of S is C, and the inverse of C is S. And those inverses are within the subset. That's why B sub 21 is a subgroup. Next, we have B sub 22. So the resulting elements are within the subset. There is a row that matches the outer top row and a column that matches the outer left column. So A, or the identity element A of G, is in B sub 22. So it satisfies the second condition. And then For the inverse, we know that the inverse of A is A, the inverse of B is K, and K is in the set. The inverse of S is C, and C is in the set. The inverse of T is the inverse of small t is a small a, and small a is in the set. And the inverse of R is R, and the inverse of A is T, small t, and the inverse of small c is S, which is in the set, and the inverse of K is B. So it satisfies the third condition. That's why B sub 22 is a subgroup. And then same thing with B sub 23 and B sub 24. So here are the subgroups. So the identity element is the trivial subgroup and the proper subgroups, and we have the improper subgroup. Now, a lattice diagram is a visual representation of the subgroups of a group, organized based on inclusion. That is how subgroups are contained within one another. At the bottom of the diagram, we have the trivial subgroup, which only contains the identity element. At the top, we have the whole group itself, since every group is a subgroup of itself. And in between, here and here and here, we place all the proper subgroups. That's it for our presentation, and follow for part 3.